So, last class we are discussing about the singular value decomposition. Suppose A is a matrix whose dimension is a m cross n, which is rectangular matrix, and this matrix A can be real or complex. Then we can decompose the matrix A into three product of matrices U, sigma, V transpose. For real matrix A, U is a orthogonal matrix. If A is a complex matrix, then U is a unitary matrix, and D is sigma is a diagonal matrix, and each element of the diagonal elements are real and positive, and they rearrange in descending order the diagonal elements, and V also orthogonal in case of A is real matrix, and it will be unitary matrix if it is a complex matrix A. Then we have come to conclusion with this derivation of all these things. Then the U columns of U are nothing but a eigenvector of the matrix A transpose in case of A is real. A into A H means Hermitian matrix, means A H means A transpose A conjugate transpose or A transpose conjugate if it is a complex matrix. That means, the columns of U are the eigenvectors of the matrix A transpose or A H. Similarly, columns of V are the eigenvectors of A transpose A, or is it a for real matrix A transpose A, or if it is a complex matrix H A H into A, and A H is what? A conjugate transpose. And sigma, about the sigma, that the sigma matrix is a diagonal elements. Each element of the diagonal elements is non-zero, or non-zero means it may be a 0 some elements, or some elements will be all elements will be positive, and these are the square root of the eigenvalues of A transpose A or A H A, that we have shown it how it is coming. Then the structure of sigma, if you see the structure of sigma, as I told you, sigma 1, this is not 1, sigma 1, sigma 2 dot dot sigma k, the next is not a sigma 0, the sigma k plus 1 dot dot sigma m. If I consider that the rectangular matrix m dimension is less than n, this that rectangular matrix whose number of rows is less than a number of columns, then it will be there, and this is your n columns, and this is your m rows, and this is rearranged in arranged in such a way, sigma, which is a positive quantity, is greater than equal to sigma 2, and sigma 2 is greater than equal to sigma 3 if up to sigma m plus m, sigma of m, because m is the number of rows in the that matrix, or the dimension of matrix m into n if m is less than n. So, now we will discuss about the system what is called H infinity norm. As we have discussed earlier also, that let us call what do you mean by system norm. System that we will describe by this. Now, singular values of this system, what is this? The system G is system, a dynamic system which is described in a transfer function matrix G of S. So, the singular values of a transfer function matrix G of S m cross, or you write it P cross m, number of outputs is P, and number of this is you can number of outputs, and this is the m is the number of inputs, and naturally the dimension of the transfer function matrix P cross m. So, the dimension of this is the transfer function of means are defined as the square root of the eigenvalues of the product of its frequency response g of j omega. We know the physical interpretation of physical what is called frequency of response of multi input multi output system, we have discussed last class, by its conjugate. What does it mean? Singular values of g j omega is equal to root over lambda I g of j omega g of minus j omega transpose. If we recollect this one, we have also for a real matrix, we have also sigma I, how to compute the sigma I singular values of this. So, lambda I, then A transpose, agree, or lambda I A transpose A, agree. It depends on whether A transpose A or A transpose A depends on the minimum of m p, m comma n. In our case, will be is equal to minimum of, you see the minimum of m p, m is the number of inputs, p is the number of inputs. This, or one can write it g I, this is I, lambda I g minus j omega transpose g of j omega. Okay. It depends on the which one is minimum out of this. So, let us call here this dimension is, this is the lambda of that one, that bracket is from here to here, that bracket is from here to here. Let us call g is dimension is what? P by m. G transpose dimension will be m by p. If p is minimum of between m and m, p is minimum, then you will use this expression. If m is minimum, see this expression, this one G transpose means m comma p and p comma m. So, if m is minimum of between these two things, then we will use this is, you can not p, you write it some other, let us call r, minimum of this. So, we can find out the what is called singular values of this one. How? You g f of s is a complex rational transfer function matrix, that is the conjugate of rational conjugate of g, this is also complex rational transfer function matrix, product of this one will be real. So, you can find out the eigenvalues of this one, and eigenvalues will be real quantities of this one. So, so I can write the singular values are positive or null real numbers. So, this symbol we are using sigma bar, maximum singular values. This is of what? The matrix G of j omega. When you are at particular frequency omega, you have sigma bar, maximum singular value, which is nothing but a, by our definition G of j omega. This is the maximum singular value. If you see that last class we have just did, this is the maximum singular value, next maximum singular value is this one, next maximum value singular, and so is descending order of this one, but all our diagonal elements are positive quantity. So, this is the singular values of g j omega, and which is maximum is denoted by a sigma bar, is greater than equal to sigma 2 g g omega. Find out the singular values of g g omega, the transformation matrix. The second maximum singular value will be less than the first singular values, that less than equal to sigma 3 g of j omega and so on, and that is less than equal to sigma m g of j omega, which is denoted by this is denoted by sigma underscore g of j omega. So, maximum singular value is denoted by sigma bar and minimum singular value is denoted by sigma underscore g j omega. Okay. So, now we can, so this is the singular value of a transformation matrix. Now, let us call system, as we are talking about the system G of S, agree, that what does it mean that this singular values of g j omega has a physical interpretation. Then what is that physical interpretation? So, this is the system transformation matrix, so which dimension let us call P cross M. So, if you see G dimension is P cross M, which we can decompose U P cross small p cross P sigma P cross M and V H, because this is, so for a particular value of g j omega, particular frequency I will decompose into this one. So, these are the complex quantity of this one. So, this is the matrix and this dimension is M cross M. Agree? So, let us call, we omit that g j omega here, g j omega, here is g j omega, this is real and this is g j omega. So, we omit j omega of this one. So, we will get it g post multiplied by that v. So, it will be a v then is equal to u sigma v h v. Okay. And this is the identity matrix, because V is a unitary matrix. So, this dimension you see P cross M and this dimension M cross M. Agree? So, now this is the dimension of this. So, what is this one? I can write it U, whose dimension is P cross P, and sigma whose dimension is M cross P cross M. So, what we can write it this in details form? We can write it this in next. G is a system matrix at particular frequency, we know g j omega. Agree? This V is how many? What is the dimension of B? M cross M. So, we have a, let us call M vectors are there, V 1, V 2 dot dot V M, and dimension of V 1 is M cross 1. This is also M cross 1. In such a way, we have a M vectors. So, that is equal to, we write it U 1, U 2 dot dot U P, and this dimension is P cross 1, P cross 1 and so on this. Into the sigma structure, as you have seen it, sigma 1 is a non-zero quantity, maybe positive quantity is a positive quantity, sigma 2 dot dot sigma P, and others are 0, 0, 0, 0, 0, 0, 0, 0. This is zeros and this is all are zeros. So, what is the dimension of that one? Dimension of that one is your P cross M. That means, this is the number of columns are M and number of rows are P. Now, you multiply, what you will get it in right hand side, sigma 1 sigma 1 is scalar quantity u 1. Next column, the second column multiplied by this, it will be give sigma 2 u 2, and in this way if you go it, I will get it sigma p u p, and other columns are 0 0 0. So, this into this is 0, then this into this is 0, and so on, last is that one. So, what is this one? If you multiply it by this u 1 by sigma 1, so this will get it a vector m cross, this is p cross 1 vector. Similarly, p cross 1 vector, p cross 1 vector, this is also p cross 1 vector. Agree? And in this way, if you multiply it by this and this, what is the resultant vector? This is p cross p, p cross m, ultimately it will come, because you have a m vectors are there like this way. So, if I equate left hand side and right hand side, I can write in short V I, G V I is equal to u I sigma I, and I varies from 1 to dot dot p. Agree? So, this we can write it. Then what does it mean this one? This is our system and V is the vector, input vector, and this input vector has a direction, because elements of this dimension of this one is m cross 1. Agree? All are, you can think of it as a sinusoidal quantity of this one. So, this is system is an input vector, I am getting u I into sigma. Agree? So, this you can write it input in the direction V I, and this dimension is just now I mentioned is m cross 1, and this one then this is our, you see, system transfer function multiplied by input vector is we are getting the output. So, this is u, you can say u is the output in the direction u I, whose dimension is p cross 1. And further, since u and v are what is called unitary matrix, then we can write u v u I Euclidean norm or second norm of u I is equal to 1 and second norm of v is equal to 1, since they are unitary matrix, and v I u 1, u 2, all these things are the column of unitary matrix, and each is what is called Euclidean norm or distance is Euclidean norm or distance or norm 2 is 1, because this u 1, u 2, u 3 are the columns of that our unitary matrix U. V 1, V 2 are the columns of our unitary matrix V. So, their two norms are equal to 1. So, that is also we can write it. So, now see this one. Note, this is important statement. Note, the ith singular value sigma I directly gives the gain of the system matrix G in the direction V I. In other words, what you can write it? So, now look at this one G V I is equal to sigma I u I. So, this is the input and output when the system is excited, G of S excited with the input vector V I, whose dimension is m cross 1, then we are getting the output is p cross 1, this output. Agree? So, now let us see this one, what we can write it. So, we can write it, this G is a complex matrix of this one. So, you write it G V I into G V I whole H transpose, because it is a complex one. So, you have to go conjugate and then transpose is what is this one. I am writing V I H then G H. Agree? So, this is an identity matrix, this is a scalar is 1, this is a 1, agree? This is 1. So, what we can write it G into G H, or you can write it same thing, we can write G V I H pre-multiplied by this G V I. So, what we can write it G H V I G H, no this no the, or what this is that one we have written. Then what we can write it that G H G H V I into V I H. Okay. Let us. So, this what we can write it, then we will write it this one. What you can write it for this one, that this equal to this one, and left hand side, this is the left hand side, sorry, this is the left hand side, and right hand side what we can write it, right hand side you can write it, you see G V I is nothing but a sigma I into U I, and G V I transpose is nothing but a U I H sigma I, because it is a scalar quantity. So, it is nothing but a, this is a 1, this is nothing but a sigma I square. So, right hand side is equal to left hand side, agree. So, what we can write it for this one, that this quantity, that we can write it sigma I is equal to square root of lambda I G H G into G H of that one. So, how we are writing this one? You see this is equal to 1 and this H is equal to this, and if you just put it this, what is that one? We got it U transpose U sigma V H, this is the G, and we can G H is what? V sigma transpose and G U transpose. Now, this and this is the identity matrix. When you are multiplied by this and this and this, it will be sigma square, sigma I square diagonal form, and it will be a, again it will be a identity matrix U transpose U H, sorry, U H is the identity matrix. So, if you take the eigenvalue both sides, then it will be sigma I is nothing but a lambda I G H. Once again I am telling you this one, we have left hand side we have written, we got it this one. What is singular value decomposition of G? U sigma V H. What is the singular value decomposition? Conjugate transpose. So, this V sigma transpose U. So, this quantity is the identity matrix. So, this quantity is identity matrix, then it is the U, and this is the diagonal form. So, it will be a sigma, this is a sigma transpose into U, and if you expand this one, you will get what is called diagonal form of that one. Agree? So, now you see the eigenvalues of this is equal to eigenvalues of that one. It's something like this is a matrix, I am doing the transformation of this one is the eigenvalues of the, and from there I can write it, it is nothing but a sigma I is nothing but a lambda I eigenvalues of G G H. Similarly, I can write it, this is nothing but a same as same we can write it sigma I G H G. How I can write it this one? Because this must be a square matrix of this one, full rank of this one. So, now this if you write it this one, this dimension is G dimension is P cross M and this G H dimension is M cross P. So, dimension P by T, and in this case dimension is M by P and this is P by M. Agree? So, G that should be a full rank of that one. Okay. So, this both the cases the singular values will be same. So, this one can see this one, if you see this one, this is nothing but a this quantity sigma I G. Now, we can write it is nothing but a lambda I G H of G is same as sigma lambda I G of G H. Now, this thing equivalently I can write it, if you see this one, this we can write V I sigma 2. What is V I sigma 2? You see you take the norm of this and if you take the norm of this, then this quantity is 1 and this quantity norm is sigma. Agree? So, sigma is what? You see from here I can write it, take the norm G of V I norm 2 is equal to sigma I U I norm 2. So, this value is 1. Okay. So, sigma I is nothing but a G V I norm G V I that vector norm 2. So, sigma I is that one, we got it. Okay. So, this divided by and sigma I V sigma I is what? V into sigma is output. So, this output divided by the input norm, V I is the input actually, so input norm and that value is equal to 1. So, this quantity I divided by 1, it does not matter. So, it is nothing but a norm of V I. So, norm of what is called norm 2 of output vector, norm 2 of input vector is nothing but a gain. So, what is gain? Sigma I is nothing but a that G I G into V I norm 2 divided by V I norm 2. This is nothing but a the output norm and this is nothing but a input vector norm. This is nothing but a input vector norm 2 and this is nothing but a output vector, this is nothing but a output vector norm 2. How I got it? Just now I told you that you see take the norm both sides of this one this and this is a sigma. If you take the norm of this one, it will be sigma I norm of 2. Agree? So, this is not sigma I is nothing but a norm of G into V I vector norm 2 and this is I got it. This is nothing but a 1 I can write V I. So, this is the output vector norm divided by input vector norm. So, you see clearly it depends on the ratio of output vector and input vector this. So, the gain of the system, how many sigma is there? Sigma 1, sigma 2 dot sigma n at by output. So, the gain depends on the direction of input vector, that V I. Agree? So, maximum gain, what you will get it? What is the maximum gain? This sigma bar is equal to sigma 1 G is nothing but a V corresponding sigma 1 corresponding vector is V I norm of this divided by V 1 norm of this, and this is equal to 1 and this is equal. So, maximum singular value of the transfer function matrix will give you the maximum gain of the systems. Okay. So, this is our conclusion of that one. So, now I will go for what is called for multi input, multi output system G of S. So, just now we have seen gain of the system depends on not only on the frequency, but also for multi input case also depends on the direction of the input vector. Agree? So, we can write it gain of multi input multi output case, multi output transfer function system depends not only on the frequency, but also on the input direction vector, V I, whose dimension is m cross 1. So, now if you have a given for multi output set, what is the H infinity norm? What is the H infinity norm of, right, it is a j omega. What is the H infinity norm of a transfer function matrix? This is nothing but a maximum singular value of H infinity norm, maximum singular value of G j omega matrix. So, in other words, I can write a supremum of omega varies from this maximum singular value of G j omega. What does it mean? H infinity norm of that one, you have a particular frequency G, I can find out the singular values of G. Out of this, what is the maximum value I recorded? Then another frequency, I will find out G j omega, which is a complex matrix rational functions. I will find out is singular value, maximum singular value recorded. Agree? Similarly, another value of frequency W is equal to W 3, omega is equal to omega 3. I will find out the singular value of transfer function matrix, and from there maximum singular value are picked up. In this way, I will sweep the frequency from 0 to infinity, and out of this which one is maximum, that will give you the H infinity norm of the system. Means in that frequency, if you place the input vector V 1 in that direction, or the system is excited with a V 1 in that direction at that particular frequency, you will get maximum gain of the multi input multi output system from the multi output system. So, it is a supremum. So, and you see the supremum is nothing but a, this meaning is nothing but a highest value of the system's gain. Okay. Let us call, I am just what does it mean this expression? I will find out that omega is equal to, let us call omega 0. Then I will find G j omega 0. For this one, I will find out the maximum singular value of G j omega, maximum singular value of this one, and this one. Let us call, next is this is omega 0 to G. Then omega is equal to omega 1. I will find out G j omega 1 and maximum singular value of G of j omega 1, and so on. You go on changing omega is equal to, let us call omega n. Then I will find out g of j omega and find out the maximum singular value of g of j omega n, omega n. And out of this all singular value, which one is maximum, that will give you the H infinity norm of transfer function matrix. This dimension is p cross m, transfer function. That means, at that frequency, what is the frequency out of all these things? Let us call frequency is omega is equal to omega x, that frequency I am getting the maximum singular value of the transfer function matrix. It means, in that frequency, agree, if you find out the SBD of that transfer function, agree, and from there if you find out the maximum singular value of this one, agree, and that maximum singular value will give you the maximum gain of the system when the system g j omega is excited with a that particular frequency corresponding the input vector V I. Agree? So, this is for multi input multi output case. As you know from single input single output case, that our for single input single output case, our g of this H infinity norm of single input single output case 1 by 1, p is equal to 1, m is equal to 1 is nothing but a supremum of omega varies from 0 to infinity real quantity, and this is the absolute value of g j omega. That means, it indicates nothing but a maximum gain of the system when you are sweeping the frequency from 0 to infinity, maximum gain of this one. And for multi input multi output case is here, for particular frequency, if you do the singular value decomposition of that transformation matrix, you will get the sigma 1, sigma 2 dot sigma m, sigma p, agree. Then you find out that what is the maximum singular value of this one, stored it. Another frequency, find out the maximum singular value of the stored it, and in this way you sweep the frequency from 0 to infinity, and out of this which one is maximum, that is the you call H infinity norm of the transfer function. Physically it interprets that at that frequency you will get maximum gain out of the system when the system is excited with a corresponding V I V 1, if you excite that one at corresponding the frequency, what frequency you are getting maximum gain of the system, corresponding V I, if you excite the system, you will get maximum gain from the system. So, this is the most important situation for the when you will design the H infinity controller for this one. So, this is nothing but a maximum gain of the systems. Okay. So, if you see this one, what I did it for this one, like that how I find out the singular values is relation with the conjugate G transformation multiplied by G conjugate and transpose or G H conjugate of G transpose. Agree? So, that is what we have seen it. Next is that what we will now talk about the our control problem. The control problem statement in H infinity framework. So, you recollect that any system we can put into this framework. We have a exogenous input, W is the exogenous input, Z is the regulated output and Y is the measurement output, which will be used for designing a controller or generating the control law U. So, it is the output feedback we are considering, and this is the our u of t, w of t, z of t, and this, and it is our p block, which is a 4 block representation, 4 block representation. Our 4 block, what sense? This is the 2 inputs, 2 output. Any system we can transfer into this structure. We are assuming for the time being that our what is called perturbation, model perturbation, that is shown by dotted delta is equal to 0, it is there, agree. So, this is 0. So, and this is this W is exogenous input. The exogenous input indicates the sensor noise, the disturbances, external disturbances, and the common input, and regulated output is states, error state, and the control state, error signal, states, and control signals, and measurement output is used for control purpose, means to generate the U. So, our this is our controller. So, now we will state the problems, what is our optimal H infinity control problems. Optimal H infinity control problem. The problem statement is a find stabilizing controller K of S that makes the closed loop system internally stable. Internally stable means all internal signals should be stable in presence of noise, disturbances, all these things stable, and minimize the transfer function T z of w of S infinity by the stabilizing controllers K s stabilizing. So, what does it mean? According to this 4 block representation, we are going to design a controller K s such that the closed loop system will be represented. If it is a state space model, it is represented, we will convert into a, that is called 4 block representation. This is a standard for program. If we have to design a controller in such a way, the closed loop system is internally stable. Not only that, we want to minimize the what is called exogenous effect of exogenous input to the regulated output. This is the regulated output, nothing but a states, error signals, and the controlled signals. This is the regulated above. The effect of W on Z, that you have to minimize. So, if you can minimize the transform, what is called transfer function, that one, then internally stable and minimize the H infinity norm of the transfer functions. What is the transfer function? Between the W to Z, between W to Z, what is the transfer function? You find out, and that H infinity norm of this one you minimize this one by selecting the stabilizing controller K s. This is the optimal H infinity control bar, but this problem is solution of this problem is very tedious. So, people are looking for a more practical solution of H infinity control problem, that is called standard H infinity control problems. So, more practical standard problem, standard H infinity control problem. Which is suboptimal H infinity control problem. This is also called suboptimal H infinity control. What is this? Again, find a stabilizing controller K of S such that K of S that makes the closed loop system internally stable. Again, only difference here in this case from optimal control problem is this statement stable such that the H infinity norm T W of this H infinity norm of transfunction between the W to Z, this will be less than some gamma, and gamma is greater than 0, gamma is positive quantity, and this is called suboptimal this statement suboptimal H infinity controller. Because this I am not going to optimize this one, I am just continuing this H infinity norm of this one will be less than some gamma positive quantity. So, that you can write less than gamma okay. Now, next is what is this? This is called the standard H infinity controller. That means, we are looking for a controller K such that the closed loop system will be internally stable. Not only that by selecting the controller, we are finding out the H infinity norm which is less than some gamma K. Gamma is a positive quantity of that one, some positive quantity. Because why you have considered this? If you consider this is, you can say this quantity suboptimal controller is more practical since other real constraint taken into problem considerations. So, because in the when you are designing controller, there may be some constraint imposed in the problem formulation. If you do this one, then we cannot do that straightway. As I told you, the optimal control problem solution H infinity controller is very tedious. So, we are introducing some constraint in the problem, and now then we are not solving the optimal control problem, but we are solving the suboptimal control problem by selecting K s in such that H infinity norm between the W to Z will be less than some gamma pre-specified positive quantity. You can write it pre-specified. This is a pre-specified positive quantity. So, next we will go for the solution of H infinity control problem. Solution of H infinity control problem. And let us call the system is described into state space formulation. We are solving this one with the state space formulation. Solution of H infinity controller, solution of H infinity control problem is done through through state space formulation. Okay. So, you know already, if you recall our earlier lecture, plant description. So, x dot is equal to whose dimension is n cross 1 is equal to A x of t plus B 1 W of t plus B 2 U of t. Agree? And this dimension I consider, if you recollect this one, this is your M 1 in cross 1, this W exogenous input dimension M 1 cross 1 and the input dimension is M 2 cross 1 and x dimension in n cross 1. So, this is the state equation x dot. Then your what is called your measurement equation, regulated output y of t is equal to C 1 x of t plus d 1 1 W of t and d 1 2 U of t. Once you know the dimension of W U, you can know the dimension of and x, you know dimension of B, V 2, A, everything. Similarly, C 1, D 1, D 1 2 you also know. So, this is our regulated output. Next is your what is called our measured output C 2 x of t plus D 2 1 W of t plus D 2 2 U of t. Once you know the dimension W, U and x, I know the dimension C 2 D 1 D 2 this. And if you recollect this one, our earlier discussion that how to describe that in compact notation from state space to what is called transfer function model. Agree? So, your state space to transfer function model, if your description is there, suppose I have a say let us call x dot is equal to A x plus B u and y is equal to C x plus d u. This is a state space representation, state space representation. Now, what is the transfer function representation of this one? G of s is equal to C S I minus A whole inverse B plus D. If D is 0 is there, so transfer function is strictly power transfer function. When D is 0, the transfer function G of S is strictly proper transfer functions. Now, this notation one can just, this is called packed notation. One model is given, you can find out the other things, state space model. So, this packed notation is like this way: A, B, C, D. That means, if you are the state space model A, B, C, D, you know, you can find out G s. How G s is required? C into S I minus A whole inverse B plus D. Agree? So, this is the packed notation. Similarly, for our this case, what is our packed notation to find out the transfer function of that one corresponding to this packed notation corresponding to our system description. Our, if you recollect that our 4 block representative P s is equal to this, a packed notation is from A, then B. B is what? our exogenous input as well as our control input. So, B 1, B 2, then our regulated output C 1, then our D 1 D 2. D is our D 1 D 2, D 1, and our measurement output C 2 is equal to D 1 D 2. If you see the partition wise, that one, this is the A matrix, this whole thing is our B matrix, this is C, and this is our D, this is the Planck matrix. And what is our P S? Once I know this, P S is what? A, C, C is C 1, C 2, then S I minus A, S I minus A whole inverse. And what is B? B is our B 1, B 2, this is our B. If you see, this is, if you compare with other case, then this is our, you can think of it, this is B, this is our C, and this is our D. Then this plus our D, D 1, D 2, D 2, D 2. Agree? So, this is our our transfer function matrix of this, whose dimension you can find out this, what is the dimension of that one. So, where again we partition, because it is a 2 inputs 2 outputs, 2 inputs 2 outputs is there, we can partition like this way, P S, P 1 S, P 2 S, P 2 S. So, we will discuss tomorrow in details all these things.